All right, good afternoon. My name is Narayan. I've been with HRL Labs for the past 15 years. I've been managing this program called Synapse. Most of you probably know about it by now. If not, that's a shock because it's been a lot of news. But what I want to talk about in this meeting here, this presentation here, is just to give you an overview of all the things we've done as part of the HRL team on Synapse. If you're interested in knowing more, I'll be more than happy to share further with you on what's going on. So fundamentally, what we're trying to do is, all of us here know about this, but essentially computers and mammalian brains and how they're different. This is just basically a dichotomy there. You can see the various points that are made here that's sort of obvious to most of you. The question is, well, if you have all these, different, if these two are so different ways of computing, then what can we do with one way than the other? And so motivated by that, Todd Hilton put together this program called Synapse. And the plot here, basically, the premise of the program was that, if I can run this, that if you had the von Neumann systems have a trajectory which really doesn't scale with environmental complexity. That is, if your input combinatorics starts to grow or explode, then your systems really don't scale and deal with it very well. Whereas hopefully, if you can build different types of systems or machines, that they would follow a different trajectory where you have a gain in terms of machine complexity, but being able to deal with the environmental complexity. So fundamentally, the goal was to seek to break the so-called machine programmable paradigm and develop neuromorphic technology that scales to biological levels. So the mantra was, model, make, measure, and you would do this over phases, and as you do that, you would sort of build more and more complex versions of the neuromorphic chips that we're envisioning to see and show functional utility of those chips as we go forward. So we had a large team. So the basic team members are listed in each of these blocks. There are 4 components to the program. There's brain architecture, which essentially sort of guides us as to what the constraints are from neurobiology that we can leverage to design the hardware as well as large-scale simulation or models of it. And then this pathway would be basically a simulation would sort of interact with an environment to sort of verify if the models that we built are useful or not in the first place. And so that will be one pathway. And then in parallel, as we build up the hardware from bottom up, meaning from the smallest of elements all the way to the more complex systems, can we also ensure that the same models that work here would also work with this pathway, that is architecture, hardware, and environment interface, and eventually, hopefully, transitioning into some real-world applications. So that is the idea. This is the team, just to summarize, and the structure. And basically, we have gone through 2 phases, and we are in phase 2 of the program, which ends in a month, about a month. And these are the team members that we've been working with. We've been selected to go on to phase 3, but that's going to be more an application-oriented effort. So I'm going to give you a sort of a very high-level picture of what we're doing in this program. So in terms of assumptions and various things we've made in this Synapse program, especially the HRL part of the program, this sort of gives you a highlight of what we're doing. So for example, network dynamics, we assume based on the team members' inputs, the neuroscience and the neurobiologists, these are the essential pieces. So Neuron Dynamics, analog computations and digital communication, which is like spiking dynamics, you can call them. Synaptic dynamics would be STDP and STP. We've heard of a lot of that during this course of the workshop. Receptor dynamics, things like AMPA, GABA, NIMDA channels that would modulate the flow of current into the neuron. Others like axonal delays, programmable connectivity, which is the brain is a small world network, so to speak, as Olaf Spons will talk about. And if you peek into any small sliver of the brain, you would find basically EI networks, essentially. Excitatory networks, which are 80-20 split, basically, is what we assume. These are the assumptions we are making when we build the chip. So the EI networks, dictated by all these dynamical elements. So when we tried to build the chip, we had to first start with something that scales. So the goal of the program was to start small, but then eventually have a scalable prototype. And so by that I mean, for example, build a chip with 10 to the 6 neurons and at least 10 to the 10 synapses. I'll talk about what this virtual means in a minute. in a square centimeter. That was one of the goals when we started the phase 0 project. And so all the elements we're building, for example, the neurons and synapses and the learning circuits, we're supposed to be able to deal with, should be able to scale to the levels that we wanted. That is 1 square centimeter housing all these elements. So when we started, we put together a framework, and I'm just zooming into one of the chips to sort of show you what it contains essentially, and I'll walk you through each of these 3 pieces. So if I have a brain architecture and I want to study it, there's got to be a way to sort of translate that into the hardware. So there's got to be a way to get the architecture into the hardware. And so we developed what's called a neuromorphic compiler. I'll talk about that in a minute. Following which, once you instantiate the hardware with a certain architecture, then you sort of make the hardware interact with the environment. And in doing so, it performs all the computations it needs to learn from the environment and then exhibit functional behaviors that are interesting or useful. So there are 2 parts to that. There's an analog core with what we call a cortical fabric, which houses all these neurons and synapses. And then there's analog memory, which stores all the synaptic conductances. And that chip basically, the crux of it, the neuromorphic computations, are those 2 elements together. Oops. Okay, so let's talk about the neuromorphic compiler. So let's say I have a small area of the brain that I want to model. Let's assume an EI network. Essentially what I have is a connectivity matrix. I have zeros and ones for the neurons that talk to each other. So neuron 1, so it's a neurons. Neuron 1 talks to neuron 1, it's a 1 or a 0, so on and so forth. What I need to do is I need to be able to translate that into sort of the fabric that I'm trying to build in order to enable my compilation into the hardware. Something happened here. Okay, before I slipped. Okay, there's a slide that slipped here. So before I go there, so the idea is one of the things we wanted to do is we wanted to do everything in CMOS technology. So that meant that we had to solve this problem, meaning if neurons have to talk to each other and they have to be directly connected by wires, obviously that's not going to work in CMOS technology. And so we proposed a time multiplexing concept. So the idea is that you have a chip, you have all the connections known a priori. What you want to do is you want to sort of break the computations, the steps into segments or time slots where part of the computations are performed, and then you stack them all up together to make the whole chip do what it's supposed to do in brain cycle time. So these guys would run at much faster speeds such that the net time taken for doing all the computations matches up with what the brain would do for that architecture. So by doing that, we were able to then develop this compiler next in order to say, okay, in which time slot, first of all, if you have an EI network, you have to place the networks in the fabric to figure out where they're going to be. And then second point is to be able to route the information, the spikes between these neurons during the instantiation of the chip. So for doing that, we came up with this compiler. All the details are in this paper. If you're interested, I'll be happy to send you a PDF of that. What that does is it enables this rapid and efficient translation of any microcircuit into this time multiplexed hardware. So just to give you a better sense for this hardware itself, imagine that you have these little circles which are nodes, and they house neurons and synapses. So N is the neuron and S's would be synapses, and synapses would also contain spike timing dependent plasticity and all the other bells and whistles that we proposed earlier on that I talked about. And the fabric would contain lines that would sort of send, or channels of communication that would be enabled through these switches that route the spikes into the node and then also take the spikes out of it. If I wanted to set those switches that way, I would take information out of the neuron to other fellow neurons. So here is a simple example of how that would work with the compiler, an example compilation. There's a video here. Before I play the video, just wanted to show you. So these are it's like a 80 neuron network. This red one is the inhibitory neuron, the yellow ones are doing the computation, the green ones are the ones that are sending signals to the system. And these little gray lines here are these channels that I talked about. And in a minute you'll see sort of red dots appearing, which are those switches, which are these, that show up for every time slot as to how the network does its interaction or communication. So if I play the video. So that's for one time slot. It would set up the communication based on what the compiler figured out for a given microcircuit. And then it would sort of quickly swap through all the slots thereby establishing all the connections you need to establish within a given brain cycle so that all the computations, all the neurons see whatever they need to see during a typical cycle. So that's how it's set up. And of course, that required adjustments in terms of how the STDP would work with those changes and so on. So the neurons are asynchronous, they continuously integrate and fire, but the STDP, we had to make adjustments in order to make sure everything works seamlessly. But it works. We have a hardware that actually demonstrates that it works. So I'll leave that part at that, and if you have any questions, I'll be able to answer that later on, maybe after the talk. The second part is this analog memory. So this is so what we decided to do is we wanted high density memory in order to be able to house 10 to the 10 synapses in a square centimeter. And the technology at the point when we started the project that was amenable to that was memristors. And so we decided to figure out how to integrate memristors with CMOS. And initially we worked with the University of Michigan to enable this. And initially we came up with an idea called, abrupt. So this is basically the memristor action. You're all familiar with that, I'm assuming. So essentially the idea is that you bias the electrodes, and there's a flow of ions through the medium here in order to establish contact with the bottom electrode. And the shape of the filament would dictate the memristance that you program into the device. It's a two-terminal device. And initially we started with an absolute version, which means once you write a value in there, if you want to reprogram it to another value, you'll have to erase it first before writing the new one in, which required extra duty cycles and more expensive in terms of power consumption. So rather than that, we came up with this incremental version of it, which is what we're using now, where you can go back and forth, up and down, seamlessly without having to worry about rewriting the device. So it can incrementally change the memristance of the device. And given the device, in phase one, we came up with this first 40 by 40 multi-level, so 3.5 bits of resolution or 10 levels of resolution, where we can actually program an array and show you fully integrated with CMOS to show actually that these arrays are feasible to make. The highlights of that appeared in the Nano Letters journal recently. And this phase, what we've done is we've taken the incremental memristors and integrated that with CMOS to actually show that the same thing we did in phase one can be done in phase two, but in a more power efficient way, where you can just incrementally change the values of the memristance without having to erase the memory in the elements. So that's for the analog memory. So now let's talk about the core, which houses the neurons and synapses. So most fundamental thing, obviously, we had to decide in the very beginning was how are we going to, what are the computations we're going to do, and how are we going to set up the system. And we all know, we decided to choose either an analog or an analog spiking, but we know there's a big difference between these two. Both use a single wire to send information in and out, but then, analog obviously has static DC power that's dissipating constantly versus the spike events that trigger a spiking system to dissipate power. And then you have this, it's susceptible to noise and variations. You need to maintain both amplitude and timing in the analog system versus just the timing for the spiking system. And then when you sort of cascade these blocks together, there's this accumulation of noise and signal degradation in analog, much more so than the spiking version. So we decided to go with the spiking, and obviously the spiking version is also biologically plausible, although there's a big debate about the coding aspect of it. So the neuron dynamics, so what we decided to do was just have simple leaky integrated fire neurons with the kinetics to support it. So if I had presynaptic spikes coming in, that would result in the channel, channel characteristics like so, where each spike would sort of bump up the current going into the neuron. If it was an inhibitory channel, you'd have a negative thing there, and they would sum up into the neuron. The neurons will continuously integrate, and the minute it exceeds the threshold, it fires a spike. So that's basically the basic mode of operation there. And then in synaptic plasticity would be basically two types, the short-term dynamics and long-term ones. The short-term ones basically modeled phenomenologically based on Markram's and Sodik's model. You all probably know about it, the facilitating and depressing sort of synapses, which are dependent on the presynaptic firing, the frequency rates. There you just modulate the conductances with the factor U that depends on a few other factors. And the other is the long-term dynamics, which depends on the timing of the pre- and postsynaptic spikes. There we have two types of functions, the excitatory STDP function, the inhibitory one, and we have both of them in the chip. So there's recent evidence that STDP inhibition is a key factor in helping keep the network balanced, the E and I balanced very delicately. And we find that to be a very useful tool in order to prevent too much of manual tuning when you set up the chip. So we have both of those kinds of STDP functions on the chip. In phase 0, given those computations, in phase 0 we started building those elements I talked about earlier. So it's first obviously the neuron synapses and STDP. We have a paper that talks about these. So that's the STDP experimentally measured curves and the spikes and so on. So the point is that we built this in 90 nanometer CMOS. It's extremely energy efficient. It's 0.4 picojoules per spike, and it consumes about 10 nanowatts per neuron. And all the details are provided in the paper. And so we try to use that to build microcircuits in phase 1. For example, this is one typical one. The paper by Song and Abbott, for example, that talks about how systems can, the brain-like networks can tune to create tuning curves on the fly. For example, if you have a ring of neurons, which are input neurons, and a bunch of neurons that are computing based on those inputs, all of them are spiking with Poisson statistics. There's an inhibitory neuron here. Over time, what happens is, based on the statistics, the neurons start to develop preferences. So, for example, here neuron number 11, which, if that is so, would sort of have this firing rate profile that is more preferential to a patch of inputs from the blue side and not others. And so these neurons slowly develop these preferences over time. But the key point is you can have two types of such networks. One is where the topology is not preserved, where the neurons are not talking to each other in the cortical or the layer that receives the inputs. And the neurons, if they talk to each other, then you can develop topologies. So we showed both of them. It's possible with our chips. So a summary of phase 1 chips, we built all these microcircuits. We built these so-called routing chips that I showed you a video for, and also memristors. But these are all built in parallel and sort of independent modules in order to verify that each of these pieces were possible in the first place before actually graduating into building a full system. So in phase 2, that's where we are now. We are putting together this, we actually fabricated this chip and we are testing it at the moment. But essentially what the chip is it looks like so. So it has it's a rectangular array of nodes. Each node, if you peek into that, contains these so-called switches that route the spikes. And it has 4 elements. The digital memory to set the switches, that is pre-programmed in a priori when you instantiate a microcircuit or an architecture into the chip. And then there's a neuron synapse STDP, STP, and then the analog memory which stores the synaptic conductances. So there's one node is that, and then we've set it up such a way that they seamlessly bud with each other into a full chip like that, as you see here. So this modular architecture has 576 nodes, 70K synapses, and the reason why, so although there's one physical synapse, we time multiplex, and so we're able to realize 70K synapses with leaky integrated fire neurons, STDP, STP, receptor kinetics, and axonal delays. Fully integrated with this time multiplexing routing fabric and configuration memory. So that's the chip, that's the layout of the chip that actually got fabricated, which is just being tested as we speak. We're expected to show the results of this testing to DARPA on 10th of April. So it looks good so far, and we hope that it will provide all the answers for what we wanted to show in this phase. So in parallel to all that hardware effort, we also have a cluster, a GPU cluster that we sort of developed or built from ground up at HRL because we wanted that particular hardware to support what we are doing particular software to support what we are doing in hardware. So this platform here would support exactly whatever features we have in our hardware and mimic it, sort of emulate it so that we don't have to be surprised when we build our models and test it in software first. So I showed you the path that I talked about earlier where we're going to do large-scale simulations to verify functional utility. And here is a paper that summarizes the work on the GPU clusters. And this can house about 40 million, it can support 40 million spiking neurons with 40 billion synapses in near real time. And this is something we are using right now to test a whole slew of models. I'll highlight a couple of them here just to give you a flavor for what we're doing. Here is one of them that is going to appear in the Frontiers in Computational Neuroscience in a couple of weeks, I believe. So this is an example of a neural model that is consistent completely with what we're doing in the hardware. It has about 0.5 million, half a million neurons and 250 million synapses, full with STDP, both for inhibitory and excitatory synapses. So imagine that you have this retinal input to an LGN, and then you have the EI network, a simple EI network modeling the dynamics of layer 4. And so the simple circuit, what we wanted to show was just with STDP for both inhibitory and excitatory synapses, and with leaky indicated fire and these AMPA and GABA kinetics, that ocular dominance maps as well as orientation, selectivity, and preference maps naturally develop. So the details are in this paper. If you're interested, I can send you a copy of it. For example, even pinwheels start to emerge, and this is all purely based on the dynamics that our chip can support. So, so this is, you can think of it as a pure bottom-up where there's no feedback or there's no action going on here. It's self-organized learning of functional maps, as we call it, orientation maps or ocular dominance maps. Now, we've also worked with, models, for example, to actually do, perform actions and have consequences for those actions. For example, action perception cycles, Christoph was talking about it yesterday. You have a system that sort of has no clue of what it's doing. It's just, for example, a 2-degree of freedom robot that's just flailing around. But there's a camera that looks at the end effector and is able to sort of, over time, learn the transformation between the motor and the visual space. This is a toy problem, but what we wanted to show here is consistent with what we have in the chip. We can actually create a spiking model that can learn from action perception cycles to perform these transformations. And in fact, we can do more than just the simple thing. We can extend this to redundant robots. We can also do multimodal transforms, which are just basically the same kind, the vanilla, because the currency is essentially spiking dynamics. So everything looks alike for the algorithms in play here. So I wanted to show you, like, for example, how this particular model would work. If I had this robot, I'll play this video. So what you see here is the robot flailing around, and the joint angles for each posture that it goes to, and these are these graphs will show you the spikes that are generated for each of those postures with constant background activity, which I forgot to mention earlier. So as the robot moves to these different postures, these spikes are generated that go into the network that I just briefly talked about. And the network is able to slowly learn a transform between that space and this space. So functionally what it meant is, was, for example, if I were to make this robot perform a tracing task, early phases of the task would be something like that, where the red, I guess the colors are messed up here, but you can see that the desired and the actual really don't match. But over time, it actually learns the transform and is able to do a much better job of learning how to do tracing, for example. So this is what was published in the paper I referred to in the previous slide. In addition to that, we also have been playing with, so that's just an example of what we've tried to work with in order to show the utility of what the chip can do. This is a problem that's probably familiar to many of you. So in the real world, when the agent is interacting with the environment, you really don't have, you have feedback, but the feedback may be delayed in a lot of ways. So recently we developed a model that can deal with multiple distal rewards that appear in the neural computation that we leverage to show how this can be used, for example. So this is an agent that has the capacity to just two actions, turn right or turn left, and it just slides back and forth, and there's a little ball that flies around, and whenever the ball hits the back plane, the agent gets a punishment. So that's the only feedback it's got, and over time, interestingly, the agent is able to figure out a way to sort of block the ball before it hits the back plane. So let's play the video just to give you a sense for how that can be done on the fly with this chip. So, oops. So initially it's making mistakes, and then over time it starts to figure out how to place the paddle or the bat or whatever you want to call it to prevent the ball from hitting the back plane. And the pace of the delivery of the ball and so on can be varied. The width of the paddle can be varied. We tried all kinds of noise with it, and it's pretty robust to many of these variations. Okay, moving on. So we tried to then do that with we played games. We sort of set up two agents like that and have a single string with reinforcement learning and make them play each other, for example. So, for example, this was a phase, we had a phase 1 dynamics versus phase 2 dynamics in terms of the richness of what we had, and sort of play this. So each of them get a penalty if they make a mistake, meaning the ball hits their side of the plane. And over time, they learn to play ping pong, if you will, without making mistakes, meaning without letting the ball through. So you can imagine that this is just a very simple toy example to show you what the chip can actually do. And in all earnestness, once we start building bigger chips with more complicated dynamics and more complex scale in terms of the number of neurons and synapses we can house, we can actually do, we think we can do a lot of interesting things with it in terms of utility. So quickly summarize, I could talk on any one of these topics for a while, but given that it's just an overview of what we're doing here, just to summarize, we've built this hybrid mixed signal circuit design that houses analog, neural, and synaptic computation elements. Digital, we chose spike transmission as the main way to scale up in terms of making it energy efficient. It's low power, small footprint. It's got flexible connectivity. We can have arbitrary connectivity programmed into the system. It's got plastic synapses. You can also have the option of fixing some of them if you had a priori knowledge and you want to use it. You can sort of fix some of them. It's got axonal delays, homeostatic plasticity to regulate the firing rates of neurons. It's got receptor kinetic dynamics. It's a scalable design. You can modularly set up these neurons to scale. We are investigating other configurations rather than just abetting in rectangular grids. We're also looking at the hexagonal type of grids that somebody else is talking about today. And currently we're porting all these models onto the chip to verify functional performance of the chip. It's just got 576 neurons and 70,000 synapses at the moment. So it only can do so much, but we are very excited by what it can do at this point in time. We've been selected for phase 3, and where we are actually demonstrating, we have a task to demonstrate some real-world applications with this chip being instantiated into hardware that flies and moves around. So with that, I'll stop, and I'll be happy to take questions. Yeah.
On slides 22 and 23, you were describing a circuit you had, a chip you had fabricated. It had a digital memory and an analog memory.
Yeah.
You said the analog transfer of memory. Did you actually have it with a memory stick?
Yes. So we have so I'm sorry if that's, pardon me? Yeah, she was asking if the memory that we built, I said capacitor and memristor, she was asking if the memristor chip was actually built or not. And the answer is yes. We actually have the memristors built, and that's based on this incremental device that I mentioned earlier, this particular. So that's the array so it's a wafer scale thing, so that's just a 10 by 10 array. And so we have it laid out on the entire wafer for the 576 neurons, and then we multiplex those synapses like I explained earlier. So yes, the answer is yes. Yeah. Yeah. So this is emulation of the chip, and right now we're actually testing because we just got the chip back on Feb 7th actually. So we are testing it. So we believe that we have exactly the same. We're able to keep sort of emulation to a degree that's very similar to what we have in the chip. So we have a very strong reason to believe that it will work on the chip, but we have to show that yet.
Are you doing registers as permanent storage or as temporary virtual synapse?
Yeah. So what we have is, so we are not using it as permanent storage. So our goal is to just show feasibility of this neuromorphic chip and the scalability of it. But in terms of actually implementing it in real-world applications, which is what we're doing now, if you want to power down the chip and sort of bring it back up again and use it, the way we are doing the membrane is that there's a retention time issue there. I mean, so there are different types of problems. So we have to deal with a whole bunch of problems there, as you very well may know about it. So retention times in this are probably about minutes before it will fade away. If you if you use an SRAM, you can probably, or it's like obviously better, but if you use other technology, that's going to be even better, like maybe, transistors, floating gate, and so on. But our goal is not really, so there are too many problems here to chew on, so we're trying to put together a chip that actually shows functional utility with all the pieces in place in terms of scaling and power and energy. Once we have that in play and we actually show that it uses those elements that we have to do something interesting, then we can maybe do the hard engineering questions later on. So that's our philosophy, yeah. Thank you.
So we're going to have a slight switch in the agenda. Kurt Larson is moving to later in the afternoon, and right now we'll have Miko Costi from the University of Wisconsin.
All right. Can everybody hear me? Is the mic picking me up okay? Okay. Thanks for the introduction. I'm very glad to be here. What I wanted to do with my time here was to tell you a little bit about the work that my group has been doing over about the last 6 or 7 years. So I'm a relative newcomer into this space, and have had the pleasure of working with a couple of very bright PhD students, Atif and Andy, and then a pretty large set of other collaborators, which has really enabled me, I think, to become productive in a relatively short amount of time, even though I came into this field knowing not a whole lot about biology or about cortical function. I just want to quickly acknowledge the support we've received from the IBM Synapse program, from Google, and from the National Science Foundation. So how did I end up in this space? So I'm basically a processor architect. I've been working on microprocessors for my whole career, for about the last 20 years. And in that space, I sort of operate between applications and technology. The interface between those two is really what computer architecture is about. And so I've been working in that space, trying to come up with new ways to improve performance and so on. And in the process of working in this space about 7 or 8 years ago, I came to the conclusion that Moore's Law was going to eventually end. We were going to run into all the problems that have been discussed here already. And we really needed to start looking for sort of new computational paradigms, new ways to solve problems that would be a better match for the technology that was coming down the road. One of the key things that I want to highlight in my presentation this afternoon is that the reason that computing as a whole has been such a successful field over the last 5 or 6 or even 7 decades is that we've learned to rely very heavily on abstraction layers. So we separate the pieces of the system with well-defined interfaces and really deal only with the abstraction layer below us and above us, And we use that to maximum effect, like is shown on the diagram here. That's not really visible because the colors aren't really coming through. But again, probably the most important interface here that we're all familiar with is the interface between software and hardware that's defined by the instruction set architecture of your processor, which is then executed by a piece of hardware that essentially implements a von Neumann machine that fetches and executes instructions. So really that's what's been the big enabler, I think, in my field. And so one of the points I'd like to make today is that I think we can learn something from that lesson, and I think we've heard similar statements already from others, so it's not really a novel statement. I'll just go very quickly through this slide. I think we all agree we need to start thinking really hard about alternative models of computation in order to keep seeing the kinds of improvements we've seen over the years. And again, biology is really the reason I think all of us are here at this workshop. And that's also been the inspiration that I turned to 6 or 7 years ago. And I think as far as additional motivation, the only additional slide I wanted to show here was, I'm sure many of you saw Ken Jennings playing against IBM's Watson a few years ago now on Jeopardy. And I think this slide sort of wraps it up. Ken is pretty good at Jeopardy. Watson is pretty good at Jeopardy. Watson doesn't really do anything else. Ken also has a life. And then you compare sort of the metrics here, 400 grams of gray matter versus 10 racks of computers, 15 terabytes of memory, almost 3,000 processor cores, 80 teraflops of computation, and 30 watts versus 200 kilowatts. It's clear that the sort of heroic AI stuff that's being thrown at Watson, and I don't want to downplay that achievement at all, it's a tremendous achievement, but that sort of the heroic AI on that side, it's clearly not going to work. Right? This is not the answer. We're never going to be competitive if we stick with this model of computation. So that really, I think, is a good motivator for the things I want to talk about. So I'm going to talk very briefly about 3 specific things. So when we think about computer architects, what do? We find ways to more efficiently map applications to technology. I've sort of done, over the last 6 years, done work in the application space at that interface between applications to technology and also in the technology space. So I'll speak very briefly about those 3 things. The first one that I'll focus on is really neuromorphic applications. So one of the things that's happened is that as we transitioned into the multi-core era, close to a decade ago now, Intel started running around and saying, well, we're going to have these multi-core chips. We have to think about new emerging applications. What are really the computationally difficult and challenging things that we're going to want to solve, the problems we're going to solve on these new platforms? And they came out with this term called RMS, Recognition, Mining, and Synthesis. They teamed up with Kai Lee at Princeton and released a publicly available benchmark suite called Parsec, which includes the benchmarks that are shown on this slide here. We've sort of roughly categorized them into classification, clustering, approximation, optimization, and filtering. That's just sort of a high-level view of what kinds of applications these are. So what's happened in my community, processor architecture, is that everyone has picked these workloads up and is running around wildly trying to optimize hardware that will be good at executing these applications. So the piece of work that, including using things like homogeneous multi-cores, heterogeneous multi-cores, FPGAs, GPUs, customized loop accelerators, etc. And what we set out to do, and this is really my collaborator Olivier Taimam from INRIA who started this initiative, was to think about, well, could we use neural net-based accelerators to tackle some of these applications? So he went around assembling a bunch of collaborators, and we sort of partitioned these applications out and looked at them and tackled this problem. And you might be wondering, well, why on earth would anybody want to look? Well, maybe this audience wouldn't be wondering this, but I think most people would be wondering, why would anybody want to look at neural nets again, after the history that we've been through in terms of the hype curve, right? If neural networks came around, there was a peak of inflated expectations, there was a trough of disillusionment where other alternatives really seemed to sort of displace neural networks, and then hopefully we're sort of on our way up to the slope of enlightenment, and maybe we'll find useful things happening here. I'm optimistic. I think we will. But so going back to this parsec suite, we went back to these benchmarks and started looking at them one by one, and it turns out that a lot of them really can be solved, and in some cases very efficiently with neural networks. So I don't have time to go into a lot of detail, but we did publish a paper a few months ago where we described these 5 applications and how we can execute them on neural networks. And since then, more work has shown that the other 3 here also work. And, you know, maybe with the exception of the video compression decompression one, X.264, that's the only one we don't have a good answer for, but the others we think can all be tackled with neural networks. And other people are.
Can I interrupt you?
Sure.
I apologize. If you could put the mic on your shirt, it's rubbing like crazy.
Oh, the problem is it's kind of oriented the wrong way doing that.
And that's just for the video. That's
Okay.
the house mic.
Okay, so I'll turn this over here too. All right, sure. Hopefully that's better. So, the bottom line here is that, you know, the benchmark suite that the people in my community and people designing systems and processors are running around as being trying to optimize hardware for as if this is the representative thing that we're all going to run on. Pretty much all of these we think can be run on a neural substrate, which, you know, sort of opens up the realm of potential applications, I think, open wide. I think there's a lot of things that can be done with the kinds of hardware systems that people in this room are interested in building. And other people, by the way, there's a very nice paper from University of Washington that looks at a different class of benchmarks, and they also show that neural accelerators map very well to them. So I'll just point to that. Application-wise, I think we're in good shape. I think there's a lot of things to look at and a lot of opportunities there. Obviously, we're not going to run, you know, our debit credit banking applications on neural networks, but I don't think that we need to. I don't think there's enough performance demand there anyway. So the next piece I really want to focus on here briefly is 2 experiences that we've had with trying to deal with, if we have applications that you know, appear to work well on neural systems, how do we take them from some sort of high-level specification or implementation to actual hardware that then deploys that algorithm in a similar way that we do when we write software for von Neumann machines. And, you know, an interesting history lesson here, many of you probably know this, is that up until about 50 years ago, there was no such thing as an instruction set architecture. When you bought a new computer, you had to write all new software for it. But Gene Amdahl introduced in 1964 the concept of a persistent ISA. And you can buy from IBM today a machine that implements the same instruction set that they introduced in 1964. It's not an inexpensive machine. They're pretty pricey, but they're still available on the market. And the real advantage of this continuity, having a clear, well-defined interface, is pretty obvious to us now, but it was a new concept at the time. It allows you to independently develop software and hardware. It allows you to safely optimize and transform the software. It allows you to safely optimize and transform the hardware without having to worry about breaking, you know, the piece of the system that's sitting on the other side of that interface. And we've obviously been taking advantage of that to great effect in the computing industry over the past 5 decades. And it seems like we should be thinking about doing the same thing. And we heard similar thoughts and similar arguments from other people already, so I won't spend a lot of time on this. But we did do some work that appeared a couple of years ago on building sort of a software-hardware substrate that would allow us to specify algorithms at a high level, run them through essentially a compilation infrastructure that would also do all kinds of optimizations on the deployed network, and would allow you to actually deploy that application, neural application, then on either a multi-core CPU, a GPGPU, or even digital logic directly. So we've had some experience in this space too, very similar to what we've heard yesterday about the COG system from HP Labs, the Pine system from the European project, and also just now at HRL as well. So the idea is, you know, you have a model, it's specified in something that looks familiar to a neuroscientist. You run it through a compiler, it maps it onto hardware and gives you good performance, sort of regardless of what that hardware substrate ultimately is. So we've done this. We've built online profiling tools to monitor it, optimize it, restructure it, and offline optimization tools to also improve the efficiency of the networks as they're deployed. And we've published a few papers that you certainly are welcome to look up, but I don't have time to get into those in any more detail in this talk. So the final topic I want to visit is related to our work with the with the Synapse project. So we were involved with the IBM team. They designed this neurosynaptic core that we heard a little bit about earlier today already. It's a digital implementation, conventional CMOS, nothing exotic as far as storage technology or logic technology, low power CMOS. It fits as described in the test chips that they built, 256 neurons per core into a pretty small die area, and really targets sort of biologically competitive energy consumption. And to get there, they really had to make strip out a lot of features that a neuroscientist trying to evaluate a neural network on this substrate might miss. So very few parameters per neuron just to minimize the amount of state that had to be stored per neuron. Synapses are binary only. All the behavior is linear, leakage is linear, integration is, so there's sort of no transcendental support at all. Very low operating frequency, so matching biological timescales, 1 kilohertz at best. But, an impressive power number, 45 picojoules per spike, which is, sort of not too far off of our actual brains as well. So the problem that we faced here and that we were sort of commissioned to work on was if you have high-level brain models that assume a much richer set of semantic behavior, and then you have this simple hardware. How do you get from A to B? How do you make these things work productively? How do you sort of bridge the semantic gap, which is a term that we use again in the computing industry community to describe the gap from a high-level language to the low-level machine code that actually executes on the machine. How do you effectively bridge that semantic gap without breaking it? So we saw some of these details, so I'll go through pretty quickly. Again, what the IBM hardware looks like. It's not terribly surprising. There are neurons, then there are axons that project to those neurons. There's some type information for each of those connections that specify the corresponding weights for each of the connections. And then there's just a connection matrix, which is just 1 bit per synapse. So again, the synapses are all binary. Input spikes come in, they get decoded, they activate a particular row in that array, and then wherever there's a 1 stored in that SRAM array, that spike gets propagated. And again, the animations aren't visible because of the missing color here, but that should have been visible here. And then if a neuron, in this case neuron 1, exceeds its threshold, that threshold then gets propagated as an output. So that's the hardware. In terms of neural models that we wanted to look at, well, like many other people, we decided to go for an HMAX-like visual model of the mammalian visual cortex, which, as I'm sure all of us know, sort of progressively captures higher level complexity of features as you move up from retina, LGN, V1, V2, V4 to IT. So I have a movie here. Hopefully this will be visible. That illustrates the behavior again of the network that we created, and you see activations in the different patches in the different cortical regions here. As you see a car coming in the retina, the car region in IT lights up, and then we have this target that is trying to identify a target and predict where it's going to be, but it prefers helicopters. So when the helicopter shows up, the target switches to predicting where the helicopter is going to go. So that's basically one example of what the network that we built is sort of set up to do. Nothing terribly surprising, but it does incorporate a number of, I think, interesting neuronal behaviors. Again, heavily simplified. We just have these little cartoon figures coming into the retina because we couldn't scale things up in simulation to handle sort of real image recognition tasks. So there's about 100,000 modeled neurons, and it does, invariant object recognition, pattern completion, motion detection, tracking, prediction, noise filtering, and so on. But as implemented, it requires complex neuronal behaviors that are not present in the IBM hardware. So this kind of summarizes some of those features. The excitatory and inhibitory connections that exist across the layers are compatible with the IBM hardware. But we also have short-term potentiation. We have NMDA, long time scale effects, and we have Hebbian learning required to learn these representations. And none of these are implemented in the hardware that we were trying to utilize at this point. So the question was, again, semantic gap, how do we bridge that gap? If we have very simple neurons, and there's good reasons to make them very simple, again, for efficiency, how do we get the behaviors that we need? So these neurons essentially just fire, propagate a spike down the axon, and then that spike gets integrated at the postsynaptic neuron. But obviously, biological neurons, as we all know, have much more complex behaviors than that. I'll go through a couple examples. If you're interested, we go through a few more of them in the paper as well. So for example, if you have an NMDA receptor at the postsynaptic neuron, the time scale is very different, right? Instead of this 1 millisecond time scale that the hardware supports, which corresponds to the 1 kilohertz clock rate, you would expect to have activation that is more on the scale of 50 or so milliseconds. So we basically set out then to build some composable circuits to emulate the effects that we're missing. So the idea here is you have a very simple basic block, building block. You only get the 4x2 Lego. What can you build out of this thing by composing sort of assemblies that have richer semantics? So to do the long time scale effects, we simply add another neuron into the path here, and that neuron wakes up and starts essentially repeatedly firing, and the repeated firing then emulates the NMDA timescale effect. It eventually dies off because it has random inhibitory spikes that arrive at it that will eventually kill it off. So that's essentially how we get there. We can map this to the IBM neurosynaptic core substrate as shown here. So essentially we just allocate an additional neuron to implement this behavior, and it spikes for us. And then we can basically start thinking about the overheads associated with modeling things this way, and start looking at the behaviors. Again, very poorly visible here, but you can kind of see that the complex neuron model that we have on the left illustrates that behavior, and then we were able to replicate something that looks quite similar with our neural assembly on the right-hand side. But there's significant overhead associated with doing this because essentially this additional neuron that we added is now spiking at every time step to emulate this behavior. So it doesn't come for free, but at least we get the right functionality. The other example I'll touch on briefly then is plasticity. So again, the particular chip we were using, IBM actually had a couple of different prototypes they built, but this one doesn't support any form of plasticity. So all of the learning is done offline in software. And then the hardware is simply configured with the synaptic connections that were learned offline. Whereas you'd like to obviously have some kind of learning in the hardware as well. And it turns out, we figured out how to do both STDP as well as Hebbian learning using the substrate as it exists. So again, if you have two neurons that fire together, you'd like to establish a connection between them that remembers that behavior. And we throw two additional neurons into the assembly to separate the presynaptic and the postsynaptic neuron pair that may or may not learn through Hebbian learning this connection between them. And again, we simply capture the coincident spikes at this neuron on the bottom. It captures that coincidence, and then it turns itself on, has a self-recurrent connection, keeps itself on again, and propagates spikes now to this intervening neuron that serves as a gate. And because these spikes are coming in now, we essentially have now created a connection between the presynaptic and postsynaptic neuron that wasn't there until we had this coincidence. The paper shows how to extend this to multiple bits as well, so you can do that as well. It's not just a single bit synaptic weight that's possible. And we see the overheads are pretty bad because we end up now having this neuron firing sort of forever. Once it's learned this behavior, it'll fire every cycle forever. So the power overhead is pretty significant. So to get this all to work, we implemented, again, sort of a compiler-like tool that takes our high-level representation of the neural network that has all these complex behaviors in it, maps them to these templates that correspond to these assemblies that provide the right semantic behaviors, and then deploy that on the neurosynaptic core hardware. The overheads, like I mentioned, are pretty significant. So if we start out with our initial design, which had about 100,000 neurons, sort of regular neurons that have some of these complex semantics directly implemented, to add these other behaviors like the long time scale feedback effects implemented using NMDA receptors, that added another 200K neurons. If we had the STP behavior, which we need for our attractor network implementation, that's another 40K neurons. And then Hebbian learning, in this case, added another 24K neurons. So for this particular network, we see about a 3.6x increase in the number of neurons, and then there's a corresponding increase in dynamic power, which is actually a lot more significant, because some of these things essentially, that neuron turns on, it stays on forever, and so you get a significant power overhead there as well. But even so, in terms of absolute numbers, we're simulating a visual network with 100,000 neurons for 3.7 milliwatts. That's still not a bad number, at least from our perspective. So I'll just conclude. I think I'm running out of time here. I talked briefly about the application space. We've done some work. Other people have done some work that indicates that there's a broad class of applications out there that can be deployed on neural networks. And these are not applications that you would normally think would be suitable for deployment on neural networks. But it turns out that a lot of times that is the case anyway. I talked about that. I talked about the semantic gap that exists between software and hardware, because biological neural networks have all these complex nonlinear behaviors in them and many, many parameters. If you have hardware that doesn't support all that, how do you bridge that gap? And I thought I'd just finish up with some open questions that at least spring to my mind as we go down this path that the workshop is trying to do, to try to build actual computational systems out of these things. What are the applications that we want to be considering and looking at? I talked about RMS. I mentioned this approximation computing work, robotics and control we've seen examples of. I think there are lots of others out there. I think a really important question is, what are the right abstractions to use, and how do we define the interfaces that provide those abstractions? Do we want a high-level interface like the COG work that we saw? Do we want a lower-level interface that's more sort of structurally oriented, like the neuromorphic ISA that we've proposed? It would be really nice to have theoretical foundations to help us on this front. I don't think that the theory just doesn't exist, and I'm not going to be the person to develop it, unfortunately. So those are important issues. Building a software ecosystem, preferably one that is available to everyone in the community and that can be widely deployed and used and collaboratively improved, I think is really important. So all these tools that it seems like every group is developing their own compiler, developing their own runtime, their own libraries, their own optimizers. It'd be nice if we could sort of pool our efforts on that front. And then I think, as far as building hardware, what are the right primitives? We've seen very different solutions proposed by different groups, even just today. The sort of very simple digital linear leaky integrate and fire neurons that IBM is building, analog like the HRL work or the work from Europe, memristor-based systems. What are all the key parameters that we need? What are the attributes that we need? What are the behaviors that we need to support? Can the sort of approach that I was just describing, can that really work? Can we get by with a very small and simple set of behaviors and synthesize more complex behaviors by ganging together collections of neurons? Maybe we can, maybe we can't. I think it's an open question. And then the learning question, I think, is also a big one. Do we want to support online learning directly in the hardware? To me, that seems kind of expensive to pay for online learning for every neuron and every synapse in the hardware all the time, when we know that synapses aren't changing that rapidly, and not that many of them are changing. So maybe there's some hybrid hardware-software infrastructure that we can develop that will get us there just as effectively in terms of functionality. And I'll stop there and take questions. Oh, go ahead.
Yeah, so you showed that you could enact plasticity on chip at the expense of significant overhead.
Yes.
Do you have a sense that you're out of ideas there in terms of, you showed us one way to do that, which seemed clever.
Yeah.
How do you know that you've hit the wall?
How do I know that I could, sorry, I missed the last.
How do you know that you've hit the wall?
Oh, no, I don't think we've hit the wall. So, I mean, basically, we were solving a very constrained problem here, which is, here's your building block, now make it do Hebbian learning. It's pretty clear that all we're really doing with that self-recurrent neuron is storing a bit. we're building this in digital hardware. You can store a bit with a latch, right? So if I could just have a latch there that I could write as the system is executing, that's all I really need, right? How do I integrate that into the high-level design? That, you know, there's some questions there, but I don't think they're hard questions. I mean, I think it's doable. But again, it was more of a, here, you only get this one Lego block. What can you do with it? That's the answer. That's the question we were trying to answer here. Carl?
You point to the large efforts that are being invested at the moment into various software ecosystems. I think you're right there. And you ask for some kind of coherence. So what is your suggestion? What do you think is the procedure to unify the software tools? Is it possible with all these very different architectures we have?
I mean, my view of that would be to standardize on an interface somewhere, right? So, for example, if you look at what's happened in processors, you know, de facto we standardized on, let's say, the x86 instruction set. And so different vendors could build hardware for it, and different vendors, including open source participants, could write software like compilers, like GCC, that, you know, have gotten progressively very good over the years. But when there's no interface at all that I can write software to, or that someone else can design hardware to, it's impossible to do that, and so we all end up doing our own thing. So we would have to come up with some sort of common interface, and it doesn't have to be perfect. These things all evolve over time, but we should have something. Somebody should put a stake in the ground and say, here's something that we can all agree on is at least somewhat useful.
Sort of one comment and one question. Comment would be, you know, that the x86 architecture sort of won a long battle, and so basically it wasn't that the industry sort of decided to standardize on it. There were a huge number of different directions, and ultimately one sort of came out on top due to competition.
Right.
So, you know, that's maybe not the most efficient way to do it. Maybe it is the most efficient way to do it. But there's a good chance that that's what's going to happen here. Let's just consider it.
I think you're probably right as far as commercial competition. Once we get to the point where there's sort of a viable market for these technologies. I mean, there are obviously viable markets for some pieces of the things we're talking about already. But, you know, is that really the model we want sort of as academics and researchers? I'm not sure that makes a whole lot of sense. And again, it doesn't have to be a fixed, static kind of thing, but it would be nice to have something to start with. But that's an excellent point.
Yeah, I'm not advocating for that. I'm just sort of pointing it out as a potential path.
Yep.
The question I have is, have you implemented or do you have plans to implement code generator for other architectures for the neuromorphic ISA?
So the work that we did there was a couple of years ago. We're not actively going down that path right now. But I mean, we did do code generation for GPUs and for CPUs and for digital direct mapping onto like an FPGA substrate, so net lists, which, you know, you can't do for everything, but certain pieces of your network, certainly once they stabilize, can be deployed that way as well. But we're not actively doing that right now. So I mean, this is basically a single PI, one or two grad students kind of effort. So we have to be selective in where we spend our energies. Okay, thank you.
Evolve machines. So he'll get it hooked up here. And then after this, we'll have our break.
recognized here? I am almost there. So I want to thank first Jim Olds for getting my display working. Is this on? And I want to thank as well Sandy and Murat, the people that organized this, Corinne Teeter and Christoph and the others at the Allen Institute. The talks in these last 2 days have been, I think, very compelling examples of the current state of the art of large-scale neural circuit simulation, both in terms of what should be simulated. And at the Allen Institute and at APL with Jacob Vogelstein, we saw really heroic efforts to serially section brain circuitry to uncover the wiring diagrams. The degree of effort that they're mustering for that reflects how important the wiring diagram must be in understanding neural circuitry, and I agree. And then separately, we've seen a number of different approaches to scaling up the computation hardware. Now, this sets up well for what I'm going to advocate in this talk, and I'll talk about the computing paradigm that I think is necessary for real neural circuit simulation that goes beyond neural networks. Nothing against neural networks and their capabilities, because they've been demonstrated, including at the last talk. It's going to entail a new type of simulation environment that's a three-dimensional voxel space in which dendrites and axons can grow and wire themselves based on local interactions during activity, during sensory activity. And I'll flesh that out in the talk. I'm then, because I was asked to touch on our work in olfaction, I'm going to talk about olfactory cortex and simulated artificial olfactory environments, plume environments, where one can put a neural brain with a simulated sensor and explore its function in a sensory motor sense. And then finally, I'll tell you about the physical sensors that we're engineering so we can come out of the simulated world and into the real world. At the heart of what we're all trying to do is to really put our finger on what's the next paradigm, what's the right paradigm beyond neural networks. Neural networks history is an interesting 50-year history driven over and over again by DARPA and other government funding. Everyone in this room knows about it. You may not know that Turing in 48 proposed neural network circuitry 10 years before Rosenblatt's first perceptron articles. But one thing for sure is that the integrative unit is simple. A weighted array of inputs that's filtered with a sigmoid of some sort is a typical paradigm, perhaps with a leak and perhaps with spikes. And there are some object recognition tasks that they can do and some that they can't. And of course, we all know about the types of biological performance that we're looking for that neural networks don't reach. Now, why don't they reach it? What are the key elements that need to be added to advance to the next paradigm the next level of performance? What's the right next paradigm for neural circuitry? Well, this is an example of a real neuron. You can see how different it is from a single compartment integrate and fire unit. It's an electrically active tree. The branches have electrical activity indicated by the color. This is a layer 5 neuron in the cortex that bursts when driven by steady synaptic input. It initially produced a burst of spikes. Now it's going to fire again. You see the activity propagating up through the dendritic tree. All of those electrical events gate synaptic events. They gate synaptic plasticity events. They gate changes in the branches themselves, and that's all part of neural computation. This is not an unusual element of really special neurons. This is typical of every neuron in the cortex, this kind of electrical activity in the branched dendritic tree. Now, I'll show that one more time because I didn't introduce it. This is if you take a look at this image, just try to, one thing I'm sure of is you may not remember all 20 of those items because they mask each other. But one thing for sure is that as soon as you saw it, you recognized it, even if it's masked by the. Now, what that means in neural correlate is that in the region of the cortex called the infratemporal cortex, which is where object recognition, object representations are found, you get an object shape dependent pattern of activity. So this is an activity of a neuron. It's the same to this star regardless of its size. But for something of very similar size, it doesn't fire at all if the shape is different. So it's a shape representation that's irrespective of position or size. That representation, that's the representation that's activated when those images whiz past you on the screen. It's activated in IT, which is from retina to thalamus to V1, V2, V4, and the 3 sections of IT. That's 7 input-output steps. So what that means is that every 100 milliseconds in IT in your brain, the pattern associated with each of those 20 objects was triggered. And there's only 100 milliseconds, and it's a 10 or 15 millisecond input-output cycle to go from layer to layer at a minimum. So that means that the representation in IT wasn't the result of computation because there are no clock cycles available to do any computation. It's the result of the input. The input triggered the representation in IT. Now, the only way that that can happen with no clock cycles for computation is if the wiring triggered the IT representation. So regardless of where the triangle or the star is, and regardless of how big it is, each retinal pattern is different. They don't overlap on the retina. And yet all those stars trigger the same distributed pattern in IT in 7 clock cycles of input-out cycles of neurons. Now, that's a wiring-triggered representation. That's really, my argument here is that that's the essence of neural computation. Not the only aspect of it, but that's central to it. So the wiring itself embeds the computation, and that really validates the great Allen Institute effort and Vogelstein's effort. I hope Jacob is still here, I don't see him. That really validates these great efforts to section cortical circuitry. That's where and that's the only way that you can uncover the specific wiring. Now, my question is now, how then, in simulation, do we wire circuits? You can't simply statistically wire circuit. You can't simply measure how frequently is a layer 4 neuron connected to a layer 2-3 neuron and then just connect them with that random probability. That won't compute anything. There's no information processing in that. The real wiring is grown during sensory processing, and what I'm going to show you is a system that we built to do that. This is what happens in the brain. This happens to be in the optic tectum of a fish, but it's the same sort of thing that happens in the cortex. What you see here are the dendrites of a neuron growing, and in green are the synapses that are present. And you see the dendrites extending and retracting, extending and retracting. Axons are doing the same thing. This is one neuron of a completely solid 3-dimensional block of neurons and axons. It's totally interdigitated. So all of this one neuron is lit up. You couldn't possibly visualize the writhing mass in 3 dimensions of all the dendrites and axons, but that's really what's happening. And that's how neural circuits initially form. That's how they grow. And then interaction between dendrites and axons during activity. There's activity prenatally in the eyes. There's retinal waves that go on before birth. And of course, there's sensory activity that comes in once the eyes open. This growing is profuse during the early stages of development, and it continues, even though dendrites and axons don't writhe around. The synaptic spines extend and retract during adulthood.
I apologize for interrupting. I don't know whether your microphone's broken quite.
Okay, I'll move it. I'll just hold it.
Are you sure?
Yeah.
You want me to fix it?
No, I'm good. Okay, so let me now describe the system that we built over a period of years to simulate this growth of dendrites and axons that happens in real neural circuits, so that we have a way to bridge the serial reconstruction of physical neural circuits with simulated wiring in the simulated circuits. In all the simulations I show you, the neurons will be branch structures. The dendritic branches will be, if you will, electrically active. They'll be nonlinear. The synapses will be not fixed, but dynamic, not just with weights, but on short time scales. Synapses change in the way a temporal pattern filters change. All of the neurons, the dendritic branches, and the cell bodies have levels of excitability that's homeostatically adjusting. Jim Olds here in his earlier round of work with his colleagues found that dendritic branches excitability changes. In these simulations, dendritic branch and cell excitability change dynamically to calibrate the level of activity of neurons, homeostatic adjustment. But I'm not going to talk about all those things. They're on board in the simulations. I'm just going to talk about the wiring and how it works, because that's the focus of what the point I want to make. So first, how do we establish the initial architecture, the dendrites and axons and their layering? So in the brain, that's driven by attractive and repulsive molecules called ephrins and the receptors to those ephrins that are studded all over the axons and dendrites of all neurons. The system wires itself. It has to have some tools to do that naturally. And neuroscientists in the field of developmental neurobiology have hundreds and hundreds and hundreds of papers describing how ephrins work. There are many overlapping different types of ephrin molecules that are distributed in three-dimensional space, and that's the scaffolding that guides neural growth. So in the simulated system, there are simulated ephrins. All of this in the simulated system that I'm describing, all of this occurs in a simulated three-dimensional voxel space. So three-dimensional space is divided up into little cubes, and in each cube is not only the concentration of an ephrin, but also a local list of what's in it. What axons are in that cube? What cell bodies? What dendritic branches? And it's that device that's the heart of what enables the system to work in real time at a computationally acceptable load. It's keeping local lists, and really this is how physical circuits wire themselves. It's all together naturally guided by nothing but local interactions. There is nothing else in a physical system. So we emulate that. This is an image of a set of neurons in the cortex of a turtle, three-layered cortex that we at Marine Biological Lab spent a couple summers reconstructing. These are half a dozen out of 80 that we reconstructed. It gives you a sense of the flavor of the geometry of the dendritic trees. We thought it was interesting and fun and important to reproduce this in the growing circuits that we built. You can see here one of the neurons in green that the simulated system grew with axons in red. Well, the red is invisible here. Is that one of the problems with this projection system? Okay, anyhow, there's a bunch of axons in red. Maybe it'll show up in some of the other movies that innervate those dendrites. What we'll also see is not only the initial coarse growth, but then later the growth of the modification of synapses during sensory experience. Well, here you see it a little bit better because the ones that are firing are in yellow. There's a bunch in red of these axons that are not firing. But this still image just gives you a flavor for the interdigitation in three-dimensional space of the axons and dendrites. Now here you've got, and again, the red's invisible, unfortunately, but there's enough yellow that you can see what's going on. The growth is happening guided by two efferent gradients, one that's north-south and another that's east-west, that guide these axons to this top strata and then from left to right. We're projecting, let's call them sensory patterns, if this was an olfactory mitral cell array. In white, these little white spheres are the thousands of synapses that are forming. This shows the pattern of connectivity between the mitral cell, which is a type of olfactory relay cell, and a single cortical cell. So these are different ways of imaging the statistics of connectivity. This can then be compared with the kind of wiring, three-dimensional wiring diagrams that can be directly compiled with these three-dimensional serial section efforts that the Allen Institute is doing. If this was a olfactory bulb and a cortex, then the connectivity statistics that we grow could be directly compared with what's measured as a way of truing up the simulation to the real world. Now here's an example of the functioning of this system and the role of homeostasis in it. These sensory patterns are by design all 75% overlapping, as if odorants that have similar molecular structure but different object associations. They're often very overlapping. In the cortex, you end up with a sparse distributed representation that's orthogonalized to different objects. And what this shows is and all the dendrites and axons are made invisible except for their tips so that you can see the cells firing underneath. What this shows is not only the formation of the synapses during the presentation of sensory activity, and some of them change, they turn on and off, they disappear, and then new connections form, if you look closely. But also, it shows the role of homeostasis in dialing down the excitability of these neurons. As more innervation, you can't build such a system without homeostatic local adjustment, because as neurons get more and more innervated, they'll have more and more input, and they'll get overdriven if they don't automatically dial down their own excitability. Now this is, instead of olfactory cortex, this is the growth of a visual cortex. That would be a thalamic relay cell projecting up to layer 4 of the visual cortex. So this will be growing 2 layers of a visual cortex. These are inhibitory neurons in layer 4. These are stellate cells in layer 4. They then project up to layer 2, 3. This is, by the way, just rendering 1/16 of the cells that are present so that this doesn't get so dense that you can't see it. In red, and so invisible on your screen, is a layer 2, 3 pyramidal cell and some of its local axons. Now when all the layer 2, 3 pyramidal cells are turned on, because they're unfortunately in black here, at least you can see them because they shadow their axons. So this gives you a little, even at 1/16 the density, a little feeling for the kind of three-dimensional interdigitation that is being simulated. Now during sensory activity, all of these branches will fire. They're electrically active, they're nonlinear. The axons fire, and different rules of conjunction of cell firing, branch firing, and action firing locally gate the stability of the synapses, not the weight. Could do that also, but the stability of the synapses. So if the synapse stability declines to, let's say, 0, that synapse breaks, that spine disappears. This really happens in vivo. That spine disappears, and then that little patch of dendrite is available for another axon. That's the crux of the rewiring. How is that axon found? Because you've got a tangled forest of thousands of them. It's found because we've got a voxel space where that local voxel has a list of the axons in it. So all that a dendritic location needs to do is to consult the lookup of what's in the voxel that it's embedded in. And it just picks an axon from the types of axons that it's entitled to connect to, because different cells have connectivity with only other certain types of cells. So, but you can see how it's a very local and rapid process to look up the eligible axons within its neighborhood. And then it gets wired to another, it gets wired to a new axon as sensory input is continuing. And in this way, the pre- and postsynaptic conjunctions that are stable self-organize, and thereby the neural circuitry wires itself during sensory input. Those can be Hebbian. In other words, if the postsynaptic branch fires at the same time that the axon is active, that could stabilize, or they could be anti-Hebbian. In fact, we evolve those different rules by which the synaptic stability is incremented upward or downward during activity. I won't show you the results, but we've also done this with visual inputs. This is a triangle representation in thalamus, if you will, that then projects upward through the system. This is the activity in the layer 4 and layer 2-3 networks. The only pyramidal cells that are rendered are the ones that are firing. Of course, there's a whole forest of them up here, but it's only the firing ones that are rendered so you can see the activity. And what we do then is just play millions of time steps of movies, feeding them up through a simulated retina, simulated LGN, and up into the simulated visual cortex. And what you find is that not only do simple cells self-organize, but complex cells self-organize, which are two of the initial types of visual representation in the visual cortex. And as I mentioned, we extensively exploit artificial evolution in finding the parameters of this system. And for that we use racks of GPUs. Speaking of GPUs, I wanted to give you a quick estimate of one of the purposes of the conference here is to talk about what kind of hardware is needed to go to the next step in neural circuit simulation. This is an argument that GPUs meet that need right now. In 650,000 neuron area, a cortical area with 10 branches each, where neurons fire at 33 millisecond frames, so it's 30 times a second if you're delivering video, and neuron activity levels are 10%. So there's 65,000 neurons active, and that is relevant because it has something to do with how much information has to be passed out of the system. With 1,000 synapses per neuron, so 655 million synapses, this is my estimate, could be wrong, but not by orders of magnitude, of the compute power that's needed, about 200 gigaflops, all this is dominated by synaptic computation. All the memory is dominated by synaptic information, synaptic state variables. All the bandwidth to feed this system is dominated by updating the synaptic variables. So if you have 20 bytes per synapse at this rate, you need 13 gig of RAM accessible to that GPU, and you need 40 gigabytes per second of data flow into the farm, into the processor core farm. It's 512 cores in one of these cards. And aside from the 13 gig of memory, right now the cards have 4 or 6 gig, but they're almost there. All these requirements are met by GPUs comfortably. In fact, of course, the flops are greater than 200. The bandwidth is probably 5 times that much. So you could do 5 cortical areas on a single GPU, and then you can gang together several GPUs. So it's a very substantial scale. And the power budget here is, it's not human brain level, but you could do 5 cortical areas of very substantial scale, 650 million synapses each for 950 watts, which is a good start. Okay, so just to conclude the first part of my talk, the conjecture that I'm advancing is that neural computation is driven by its wiring. That example when 20 images were flashed in front of your eyes shows wiring-triggered representations. There's no computation in 7 clock steps. It has to be wiring-triggered. The Allen Institute and the APL effort are going to give us the wiring diagrams at great cost and great effort. But right now our neural circuit simulation systems don't wire themselves. That's why we built the system. I'm going to pivot now because we're applying this primarily in olfaction, in artificial olfaction, and I was asked to to talk a little bit about that as well. First of all, I'm interested in both the visual cortex, the neocortex, and olfactory cortex. Here's one reason why. This is a cross-section of a turtle brain, so it's one half of the brain. There's the other half would be over there. This is a two-dimensional cross-section. This is the middle of the brain. This is the cortex. It's called the pallium in the turtle. This is the olfactory cortex. In white, you can't really see it too well, or the layer 1 where all the inputs come in and out. And then in dark, this is a Nissl stain. In dark are the cell bodies. Now, I put this up for one reason. This is, right here, this is the visual cortex. And this is V2, if you will. And you cannot tell the difference between them. There is no difference between them. The cell firing properties are identical. The cortical circuitry, to the extent it's known, the cortical circuitry is identical. It's a module that evolved in reptiles, that is used extensively in reptiles, not just for olfaction, but also for vision. Then in mammals, 3 more layers were added. That's why this is a good case for a simpler evolutionary precursor of cortex that's relevant to cortex, because this is what cortex evolved, this is what 6-layer cortex evolved from. Now, we don't have to study turtles, we can also study mice with all their genetic benefits, because mice have olfactory cortices that look in Nissl stain very much like that. In mammals, olfactory cortex is still 3-dimensional. So this is a simulation of an olfactory world. This is a plume. It's coming out of this trash can here. This is actually simulated in a physical room with air conditioning in ducts and exit vents and door jam, and there's a window somewhere that's got a different temperature. It's a really, really physical simulation, 2.5 million finite elements in it. First of all, it shows you that these plumes are not, odors don't radiate as a 1 over r squared sphere. They're very turbulent, and in fact, this odorant is heavier than air, but it's the convection inside the room dominates its movement. So this is very typical of the olfactory world. If you're a robot at 12 inches above the ground, this is what you see. Or if you're an animal, that's what you see. So you have to explore this plume over time in order to find the trash can, in order to function. So what we've built is simulated environments where plumes like this are simulated to interact with simulated robots, where we can put a neural brain on board. Because what we want to do, and the questions have been asked over the last 2 days, how do you get some traction with the real world here with these neural simulations? What sorts of activities should you ask them to perform? And how can you improve them, and how can you test them? Well, sensory motor performance in the real world is what neural systems evolve for. The olfactory circuitry is simpler, but as I argued, evolutionarily related to the neocortex very directly. So what we've chosen to do is to develop simulated worlds with olfactory plumes where a robotic agent can move through it, have a simulated sensor activate a simulated brain wired up like I showed you, to then control the motion of that robot in the plume. That's an example of a robot. I'm not going to, there's a little video there, but it's not really important. Okay, so here's a simulated plume. This is in 2 dimensions. We looked and we found a simulation that could run in real time. So it's computationally light, and it makes some compromises, but it still looks like 2 different jets of smoke of different colors interacting with each other. Okay, now we added something to this, and this is all published in a paper in Frontiers in Neuroengineering a few months ago. We added something, we pulled off something here that hadn't been done before as far as we know. If you're going to do a simulated robot moving around in a virtual world with plumes, the fact is that real animals perturb the plumes that they're in as they move through them. And if you're going to really test your simulated brain in what you think is a real world with nice plumes, your animal or your robot, as it moves around, controlled by its simulated brain, has to perturb the plume. So you have to have a dynamically updated finite element simulation in real time. And you can't see unfortunately, you can't see the red plume, just the blue plume, because of the, so there's two plumes here. That's prior slide, there were two different colors. The red's just invisible in this projector, unfortunately. But you can still see, then it's jetting out from some photon torpedo. It's got a third color that it can jet out just for fun. But you can see that the robot is perturbing the plume, and you can joystick and move it around in real time. One thing that brings to mind is this is the reality of the olfactory environment, is that the olfactory signals are very chaotic. And so you need to have repeated sampling at a high rate, like animals sniff, as you move through these simulated plumes in order to gather the information that's available. This is a plot of 3 different colors showing 3 different object smells, concentration at the sensor location as the robot moves through the environment. So if you're ever going to do this with a real robot, you need a sensor that has a short time constant. So now I'll show the whole thing in action. Here you don't see, unfortunately, you can't see much of anything here, but there's a robot going through these plumes, and there's another color plume here. And as it hits the plume, it activates these sensory neurons, these mitral neurons, and finally these cortical neurons are activated. And when the cortical neurons are activated, as you see just there, the motor neurons fire, and that controls the robot, which then pushes it around in the virtual world. So this is an example of this closed loop. Now the last thing I'll talk about, and I hope you see different elements are all connected logically. The last thing I'll talk about is the work that we're doing to engineer a sensor that would allow us to put these brains on real robots, on that little track robot that I showed you earlier in the talk. Of course, we don't want to simply relegate ourselves to simulated worlds with these simulated brains. We want to put our simulated brains in real machines. In other words, we want to build neural machines. For that, we need an olfactory sensor, physical one. So we've engineered one. Well, this is the robot being, oh yeah, this is, I won't try to explain this too much. This is actually a physical robot guided by the brain signals coming from the simulated brain. So this is an intermediate stage of putting a neural brain on board a physical robot. This physical robot doesn't have the olfactory sensor. So the robot that you can't see that's in the virtual world, when it gets hit by an odorant, it activates its brain, simulated brain, activates its motor neurons. Those motor neuron signals are driving the tracks of this little physical robot. So you can integrate the virtual world and the real world in these, of course we want motor control that's relevant to a real world robot, and this is a way to have that on board, not just have a purely virtual world robot. Okay. The last thing I was going to tell you about was the sensor. So what kind of sensor do we need for this? Well, anyone that is familiar with neural olfaction knows that it's a high-dimensional representation. The dog has 900 different olfactory receptors, largest gene family in the genome. Insects have about 100, humans have 350. So the initial impact of an odorant is to activate in the human this 350 different olfactory receptor types. So it's a high-dimensional vector. So the simulated, the physical artificial olfactory sensor also needs to be high-dimensional, but I argued before that it needs to be rapidly reversible. It has to be rapidly reversible so as the robot explores the environment, the different, as it interacts with the plume, it, like animals sniff at a high rate, it also has to interact with the odorant landscape at a high rate. So here's actually the chip. So this is not just one day we'll do it plan. We've engineered a chip. This is generation 1. It's about 3 years ago. This is, these are carbon nanotube transistors that are functionalized with coatings of single-strand DNA. And what's quite good about this is that the response, this is the current response as methanol is presented. The response is DNA sequence dependent. So these 3 transistors were coated with 3 different DNA, single-strand DNA oligos. They all had the same letters. There's the sequence, then here's all the same letters alphabetized, then here's a random reshuffle. So those 3 different coatings responded to methanol in these 3 different ways. That's a little taste of the fact. You can imagine how many different transistors you can create with coatings of the different DNA sequences available to you. You know, it's a boundless kind of a dimensionality that's potentially available. The other thing that you see on the very same slide is this is very nicely reversible over and over again. In fact, the DNA coating is really durable, and because the DNA occupies the covalent functionality of the nanotube, there's just van der Waals interaction with the volatiles, low affinity, reversible. So even though these are pulled all the way to equilibrium, it takes about 5 seconds, 10 seconds. Shorter SNFs have faster on-off rates, and you can get to seconds of clock speed in refresh. So, yes?
So are you using DNA sequences to create signals from van der Waals interactions with odorants and not relying on the specificity of the DNA bases themselves and pairing?
Exactly, yeah. These are interactions with odorants, which are not DNA, but rather small molecule volatiles. And so this is not a hybridization. This was dreamt up by my colleague Alan Gelprin at Monell, once at Monell. This is the architecture of this sensor chip is as follows. There's a schematic of one carbon nanotube FET. In between source and drain are nanotubes. They're coated with DNA in a very simple way. Just put a little drop of water containing the DNA on it, let it sit there for a while. We cluster these because you want to get the benefits of averaging just like the biological olfactory system does to improve sensitivity and improve signal to noise. So we average here, this is an array of 16 identical FETs, all coated with the same DNA. There's some variability in carbon nanotube FETs, so this averages the variability and it also just improves sensitivity. And now here we have the chip schematic, which is an 8x12 grid of these clusters of 16. So we put a little drop of DNA solution, in principle a different sequence for each cluster. So this then would be a 96-dimensional vector of response to a volatile. This is the actual chip, zoomed in at 3 scales. So the transistor, the cluster with its interconnects, and then the chip itself. Again, this is a 3-year-old generation. And this is my next to last slide. You can't see the red, so all of this you can only see in shadow. The point is that I wanted to bring you back to, because the most important thing I wanted to bring to the meeting was the neural circuit simulation environment for simulation of the growth of dendrites and axons and their wiring. And this just shows the architecture of this would be an olfactory bulb and olfactory cortex. The point is that it's a perfectly general purpose simulation environment, and any neural structure can be grown. Earlier I showed you a visual cortex grown. This is a olfactory bulb and cortex grown. So just to conclude, I made the argument that the wiring of neural circuitry is the missing piece in our work, and it's at the heart of the functioning of neural circuitry, really neural circuitry. I've shown you a system that self-organizes the growth of the circuits and their wiring during the presentation of sensory information, and I've described it a little bit. what I wanted to announce is that we want to make this simulation system available to any academic research group that would like to try using it. And I think with that, I'll close and thank you for your time. John?
So just to be clear, in normal olfactory receptors, presumably that's a protein-based receptor for an odorant?
Yes.
Okay. So the fact that you discovered that there were chemical interactions with DNA, presumably that was just a random observation that you decided to take advantage of?
It was just a conjecture that actually it was first used with single-strand DNA complexed with a fluorophore. So there was the readout was the flashing of the fluorophore during binding. And then Alan thought, gee, what if we put these on transistors? Because he had done transistor olfactory sensing with other functionalizations. So it is not to say that there's not a similarity suggested between the oligo and the business end of an olfactory receptor. But it works mathematically in the same way, in that you get a single oligo responds to many different odorants. The single odorant will light up many different oligos, so you get a pattern in response to any single volatile. I'll get this guy right here, and then you, Jim.
There's a chance if you took random DNA, you might actually span a much lower dimensional space with the DNA. Have you clustered the responses from random DNAs, and do you have a sense of dimensionality?
Well, we have a sense that the dimensionality is huge simply because if we take 5 or 10 different random DNA, we get a pretty lively responsiveness to a range of different things. And given the infinite size of that space, it's got to be like the odorant receptor response to volatiles. It's got to be a pretty dense representation. But we haven't mapped its architecture. We'd like to. Jim?
How does the neurite on either side of the putative synapse have a lookup table biologically for what's in its voxel perimeter?
Well, good question. It just, if a synapse breaks, that piece of dendritic real estate is available for a new synapse. And as Jim knows, one thing that's remarkable about neurons, if you just quantify them, is that their number of synapses per unit dendritic area is totally fixed across the whole dendritic tree. That's a unit of real estate that's optimally used. So if there's a spare patch of dendrite that doesn't have a spine, it's going to get one. And the way it does, to answer your question, is filopodial search. So any axons that it can touch, it tries to make a candidate connection with. Please?
This is spectacular work. Congratulations. I have a question concerning your synapses, which obviously are important. You say you need 20 bytes to code a synapse. Can you tell me what you need 20 bytes for? Because a lot of information.
Yeah. So our synapses have, they can have both AMPA and NMDA properties. They have a temporal eligibility. In other words, there's a window in time during which events occur that has to be clocked because the degree of interaction and plasticity fades with time. I could go check what that list is. We came up with the 20 bytes. And if that's a generous estimate, then that means that the GPU hardware has that much more capability. John?
So it's a different piece of your talk, but when you're wiring up these systems, it sounds like there is a spatial element of it, but is there anything equivalent to, say, chemical directedness that you might expect to guide interactions between specific neuronal types?
There is. I mentioned that briefly. We put simulated efferent gradients, and here's a movie of growth where I've shown the efferent gradients explicitly. There's a gradient that goes from 0 to max at this plane, and then here the density of efferents doesn't change. And so this growth, which is attracted by the gradient, now becomes isotropic in this layer. And then there's another gradient from left to right that draws these axons. So yes, there is, and I mentioned it briefly, that the coarse wiring is initiated with sets of efferent gradients that have a geometry that grow in an attractive or repulsive nature, that grow both the dendrites and the axons. You had a question?
You alluded to actually learning weights, not just learning whether or not the synapses will die or maintain. Have you actually done that in simulations, or just in theory you should be able to?
Well, the system can accommodate weights that are either binary, which most of our work is with, or weights that are real value. And the weights can be modified by the same type of local rules that modify stability.
So you're able to store real value weights with the 20-bit synapse?
Yeah, actually we, because all this is stored on the GPU, and we want, one of the key constraints in GPUs is not the total storage, but the storage that's in the cache that's local to the compute element, the processor. And that's what's tight, or at least last time we optimized it, that's what's tight. So we actually do double duty. If you have a Hebbian rule for strengthening the connection, you could also have that same rule modify the weight. And so we actually, in this work, if we turn on modifiable weights, we have the weight actually have the same value as the stability. But that's not necessary. That was just an optimization. It's straightforward to have two different parameters. One is the stability of the synapse, one is its strength. Please?
Just a question related with plasticity. What you have implemented is just something like STDP, or you have also the possibility of implementing synaptogenesis or similar structural plasticity?
Yeah. Well, we have structural plasticity as the central feature here that I was talking about. So you could say it's synaptogenesis. We have synapse replacement with search from that location of the dendrite in the local space, the voxel, which is, again, very much what physically is done with a filopodial search for another axon to connect to from the dendrite. What was the other part of your question?
No, that was related with structural plasticity, and then about plasticity, just synaptic plasticity, not structural.
Sure. So as I was answering to the prior question, it's very straightforward, of course, to have local interactions of cell firing, branch firing, and axon firing. You had asked about STDP. That can be implemented. That's the need for the counter that takes up some of the synaptic memory requirement. The synapse has to know how long it's been since it was fired. And not only STDP, but we also have explored the use of temporal windows for plasticity, axon eligibility windows. That's all of these events can have durations in time that can be monitored locally.
And all this is learning those 20 bytes you were mentioning earlier.
Yeah.
Okay.
In fact, that's why that's what pushes that memory, is storing the local time history for the synapse.
Thank you.
My pleasure. Yeah?
Simulating only one type of neuron?
No. Each neuron type, unlimited number of neuron types. You add another type, specify its dendritic structure, specify its excitability parameters, and its homeostatic targets for adjustment of excitability during activity. All the parameters are neuron-specific and synaptic connection-specific, which means a connection is defined by its pre- and postsynaptic partner, and the properties of the connections themselves can be different for every different pair of neuron type.
Are you able to set up both spiking and non-spiking systems with this model?
Yeah, I mean this is a spiking system, as you can see. You see these things flashing, and so if you were to convert it to a non-spiking system, you would just impose time durations for the action of a spike. and for the emission of a spike, you would go from single events that are thresholded to conveying average rates. And we've considered that, but it's not, that's kind of going backwards in terms of neural fidelity, so we haven't actually implemented it.